Hey everybody, I hope you're enjoying your day off. I just want to quickly run through some notes and just kind of review Kirchhoff with you today. I want to sort of warm you up real quick with this slide. We've done resistors in series and parallel, and we've talked about galvanometers and voltmeters and ammeters, but I just want to sort of use this one as kind of a brain warm up if you've been sleeping until now. Take a quick look at these three circuits. Which one of these could you easily analyze, or which ones of these could you analyze just using the rules for series and parallel resistors? And intuitively you're like, oh, wait, which one of these is the one you can analyze? And you might intuitively say, oh, A is impossible. Well, the other ones are not so bad. But I want to take a quick look at A together with you. You can actually redraw A in a fairly simple way. If you take a look at it, I don't know where to draw on here. I'll put the battery over here. If you start out with the battery here and then work your way through, this first resistor right here is just connected to the positive terminal. And then from there is where it gets a little bit messy. You can see it reaches this terminal point right here and then splits into 1, 2, 3, 4 paths. I'm going to draw these up here just so we get a little bit more space. The first path down this one here just returns through this one resistor back to the other side of the battery, which I'll draw over on this side here. So that resistor just goes across like that. And that's not so hard to analyze. This next set here goes through this resistor and then this resistor back to the battery. And you're like, okay, that's not so bad. So resistor, junction, resistor, back to the battery. That's these two. Now you might notice these two right here. This one goes from that junction through here, back to this resistor, back to that middle junction. So this gets a little bit messier. Resistor, junction, resistor, and then back to that junction over here. And then the last two, sorry, it's getting a little messy. Resistor, resistor, and then connects back to here. Believe it or not, you could analyze this, find these two in series and parallel with that, which is then in series with this, which is then in parallel with that, which is then in series with this, which is in parallel with that, which is then in series with this. And believe it or not, yes, you can analyze A. B is also simple to analyze. You've got these two resistors in parallel, which are then in series with these two resistors in parallel, which are in series with these two resistors in parallel. The one that you cannot answer is C. Believe it or not, this middle resistor here makes this one almost impossible to solve. All right, moving on. Let's see, should we do this one? You've got two resistors connected in parallel. What's the equivalent resistance? How much current would supply the network and how much current would flow for each one? This one, I'll just draw it real quick so you can sort of see it. It's not that bad. You've got two resistors in parallel, a 47 ohm resistor, oops, and a 33 ohm resistor. And you could very quickly realize, oh, there's 12 volts across each one of these. And so you could very quickly solve the current for each one and then the total current flowing out of the battery, which will be the sum of those two. Moving on. Potential difference between 2 points. We kind of worked through this already, or a little bit about this. I just want to quick review it. If you take a look at the circuit up here, let's start and let's, by just arbitrary definition, define point A as 0 volts. By the time it goes through the EMF, we're at 12 volts. If you solve the current in this circuit, you'll see that the total resistance, the internal resistance of this battery, this is this part right here, is 2 ohms. External resistance 4 ohms. Total resistance is 6 ohms. And you can figure out, oh yeah, the current in this circuit is just going to be 2 amps. If there's 2 amps flowing through this circuit, what's the voltage drop through this? Well, if you remember, voltage drop is just equal to I times R. In this case, 2 amps times 2 ohms. It's going to be a 4 volt voltage drop. We were at 12. By this point, we're at 8 volts. Still at 8 volts across all the way over here. Remember, wires don't have any resistance in this class. And then what's the voltage drop if we have 2 amps again flowing through this 4 ohm resistor? Again, delta V is equal to I times R. And of course, you end up with 8-volt drop, we're back down to 0 volts. Oh yeah, that makes sense. All right. And yeah. Oh, what's the terminal voltage on the battery? If we hooked up a voltmeter to this battery, we would discover that, oh yeah, sure enough, this voltmeter would only read 8 volts. Why? Because of that 4-volt internal drop for that internal resistor. And so if you look at it, you can sort of quick solve it. I'm not going to do this one. Here's a circuit. You can actually map out the potentials at each point. You have a potential drop for each of the resistors, which is this little slope part, and then batteries can actually increase the potential across themselves. But you know that the sum of all the potential gains and potential drops has to be 0. It's one of those loop rules from Kirchhoff. Take a look at this. Here's the circuit we just did. Remember, we had decided that this was going to be 0 volts. And remember, the current was 2 amps, and this is the same as the one we just did. This symbol right here, again, remember, it means ground. That means we connect it literally to the earth. And we always assume that the earth's potential is 0 volts. But what happens if you put the 0 someplace else? Well, it makes it a little bit interesting. You can actually put it anywhere you want. It just gives you some weird results. Remember, we had an 8-volt drop through this? So if we're at 0 volts and we drop 8 volts, what's the potential here? The answer is negative 8 volts. And again, we're at negative 8 volts right here. The battery gains us 12, so now we're at 4 volts. And what's the voltage drop through this? Remember, that's 4 volts, and so now we're back at 0 volts over here. Yes, it still works. You're like, wait, but this is confusing. Yeah, I get it. You can put the ground anywhere you want. On the AP, they do this sometimes just for fun. You're like, strange fun. You can also calculate the power output of each part of these. You can calculate, in this case, what's the battery's power output. If you remember, there was 2 amps there. The power output of the EM cell is 24 watts. And you can calculate the power output of this internal resistance. Let me write EMF on this one. The power loss through the internal resistor, I'll make that small r, would be, I'm going to use I squared R in this case. 2 amps squared times that. We have 8 watts of heat generated in this internal resistor. And how much power loss is in the external resistor? Again, using I squared R. In this case, 2 amps squared, 4 times that, 16 watts on the outside. Do you notice something? The power or the heat being generated by these 2 resistors is exactly equal to the power being generated by the battery. And that's the big idea, that the sum of the power outputs, the heat generated, always has to be equal to the power that the EMF actually generates. 8 plus 16, 24. Multi-loop circuits, yay! Involve Kirchhoff's rules, and this is the quick review part. The junction rule, the sum of the junctions going into any junction is equal to the current coming out of those junctions. The loop rule, the sum of the potential gains equals the sum of the potential drops. Actually applying those gets a little bit long. Yeah, I know, screen save this one somewhere if you get a chance. But most of you are pretty good about this already. How are we going to do it? Let's analyze the circuit. So take a look at this one. The first step is to guess the current. And in this case, they actually guessed the current for us. They said the current going down this way for this resistor is I1. The current going down for this resistor is going downward. It's going to be I3. And the current for this resistor is upward. And it has a magnitude of I2. And we got 2 batteries. This battery is trying to force current around this way. This one's trying to force current around that way. The junction rule actually allows us to... we could write at this point 3 equations. One for this loop, one for this loop, and one for the outside loop. And we could solve the system of 3 equations. But before we do that, let's take a look at this junction real quick up here. This junction here, we've got I2 coming in. Remember, you can't lose current anywhere around the circuit. So this is I2, the current coming from the battery is I2, going into junction I2. And we have I1 heading out this way. So instead of writing I3 down here, we could write this instead as the current here would be I2 minus I1. Why? Because the current coming into this junction is going to split up. Part of it's going to go this way according to the way we drew it, and part of it's going to go this way. What's left? We have I2 coming in. Part of it goes out as I1. The remainder down here is just the difference between those two. Yeah, you could have also looked at this junction, but you get the idea. Writing our equations for this one, you can choose any of the loops. And I don't know, I'm just going to do the inside loops. I'm going to work around this loop this direction. Remember, you can choose any direction you want. And over here, I'm going to work around this loop in this direction. Both of them counterclockwise. Writing the two equations, for loop number 1, you can start anywhere you want around this thing. I'm going to start right here. The voltage drop through this resistor, we're going through it in the direction of the guess current. So that's going to be 2 times I1. And now working way around here, the other voltage drop would be 4 ohms times the current here. But because I'm going backwards through the direction that we guessed the current, instead of a voltage drop, it would actually be a voltage increase. So negative 4 times I2 minus I1. And now going around the rest of the loop, we go through this battery in the direction that it's trying to force the current. So the sum of the voltage drops has to equal the sum of the voltage gains, which in this case is positive 12 because I'm going through it in this direction. Simplifying this one real quick, we've got 2I1 plus negative, whoops, what did I just write here? Sorry, that should be a 1 down here. Negative 4 times I2 minus I1. Negative 4 times negative I1 is positive 4I1. So this equation becomes 6I1 minus 4I2 is equal to 12. Just to make it a little bit easier to see. All right, loop number 2. Loop number 2 looks like this. Working around it, I'm going to start with this resistor here. So the voltage drop through this one, 4 times I2 minus I1, because I'm working through it in the direction that we guessed the current. And the voltage drop through this one is going to be 3 times I2. Again, positive because I'm working through it in the direction. Oh, wait. Whoops. Yeah, working through it in the direction I guessed. Equals the battery voltage. Now this time, I'm working this way around the loop, which is against the direction the battery is trying to force the current. So I end up with negative 6. Solving this one, I end up with, let's see, negative 4I1 plus 7I2 is equal to negative 6. Now, if I can remember those numbers, whoops, 4 times I2, there we go, equals 12. Plugging that into your Inspire, you can very quickly calculate it. Should I show you that? Yeah, why not? 6I1 minus 4I2 equals 12. All right, oops, sorry, jumping over here. Turning on my handy-dandy calculator. Let's keep those equations there. Menu 372, and let's go down here, and just to make it a little bit easier to understand, let's call our first variable I1 and our second variable I2, just to make it really easy to understand what we're doing. Say OK, oops, enter. All right, and our two equations, 6 times I1 minus 4 times I2 is equal to 12. And our second equation, negative 4 times I1 plus 7 times I2 is equal to negative 6. Solving that, we get this. So 30 over 13, 6 over 13. Remember that? 30 and 6 over 13. So back over here, over here, whoops, I'm running into everything here. I1 is equal to 30 over 13 and I2 is equal to 6 over 13 amps. Make sure that's right. Yes. And so what's the current then through this one? Oh, that's interesting. So that middle current for the 4 ohm resistor would be 6 over 13 minus 30 over 13, or negative 24 over 13 amps. What does a negative sign here mean? It means, oops, we guessed the direction of the current wrong. The magnitude's still correct. The negative sign here just means that the current is flowing opposite what we drew it. And that happens. And that's why people stress out when they guess the current. What if I guess wrong? It's okay. You'll just end up with a negative sign here. And I think we're good on that one. I think I actually have the answers on this one. Let me go check. And oh yeah, we got the right answers. Good. So if you take a look at these you can actually solve without Kirchhoff. Why? Because all these resistors are in series and parallel. And so even though they look like multi-loop circuits, because you only have one source of EMF, you can solve these just with the series and parallel ones. You don't have to do Kirchhoff. But ones like this where you have multiple sources of EMF, yeah, you do need to use Kirchhoff. And let's go ahead and solve this one just real quick so you can sort of see it. I'm just going to quick write the voltages. 3 volts. R1 is 2 ohms. These are, wait, okay. R2 is 4 ohms. All right, so we've got a bunch of these. 2 ohms, 2 ohms, 2 ohms. And this is 6 volts here and here. All right. So, again, they drew the currents for us. Again, just they guessed it for us. They may or may not be right. I'm going to use the junction rule at this point right here. We've got I1 and I2 coming in. I'm going to rewrite this as I1 plus I2 because that has to equal the sum of those coming in. Working around the junction, since they sort of drew it this way, I'm going to work around this one first. That's loop number 1. And looks like the easiest way around this one is going around this way. That'll be my loop number 2. Solving this one, first of all, equation number 1. Just solving it, working around this loop here. I'm going to start at the top here, and so we've got 2 times I1, and then we've got this one, which will be the voltage drop through it, 4 times I1 plus I2, plus the voltage drop through this one, 2 times I1, equals the EMFs in this loop, which in this case is only the 3 volts, and it's going in the same direction. Solving this one, we've got 6I1, 8I1, plus 4I2 is equal to 3. All right, in loop number 2. Solving this one, I'm going to start at the top of this one right here. So the voltage there, voltage drop 2 times I2. Again, I'm going in the direction that we guessed the current. Voltage drop through this one, plus 4 I1 plus I2. Let's see, and this resistor over here, plus 2 I2. Again, we're going all these in the direction that we guessed the current. Equals the battery voltages. Let's see, I'm going through this one in direction, so positive 6, and then this one, oops, going backwards, negative 6. So I end up with 6 plus negative 6. Simplifying this one down, oops, that should be a 2 over here, sorry. We end up with 4I1 plus 8I2 is equal to 0. Solving this one, grabbing my handy dandy calculator and moving it around a little bit here so I can see it. Let's do that again. menu 372. Whoops, whoa, how did I do that? Escape a little bit here. Sorry, calculate, yes. Went too far back. Oh, let's cheat a little bit. Let's grab that and just go back and edit it. Let's see. So one of the equations, 4 times I1 plus 8 times I2 is equal to 0. And our top equation, we end up with 8 times I1 plus 4 times I2 is equal to 3. Double checking my writing here. 8, 4, 3, 4, 8, 0. Solving this one real quick, we end up with, fairly interesting answers. 1/2 and -1/4. So that's that. And I2, -1/4 of an amp. What does that mean? It means I guessed all of these currents backwards. The current's actually going this way for this one, this way for this one. And what's the current for this middle resistor? It's just the sum of those two. So the current for this middle one is just going to be 1/2 plus -1/4. It'll be +1/4. And since it's positive, it is in the direction that we guessed. At this point, you should be fairly comfortable with actually solving these. They're not too bad. Enjoy, and good luck with this, and we'll go over any questions you have next time. See you soon. Bye.